very good evening to all. We hope that you had a great Nicomas term so far. To wrap up the speaker line for the term, today we have with us Sir Michael Pender. So Michael founded and managed the semiconductor physics group in the Cavendish that is at the forefront of today's semiconductor research, and is currently Pender Chair of Nanoelectronics at University College London, UCL. So Michael is best known for his work in condensed matter physics, pioneering the study of quantum effects seen in low-dimensional electron gas systems, which have been important in the development of semiconductor-based nanoelectronics. His awards include the inaugural Mott Medal of the Institute of Physics, the European Physical Society's Europhysics Prize, the Institution of Engineering and Technology's Fabre Medal, and the Hughes and Royal Medals of the Royal Society. And he was knighted in 2006 for his services to physics.
Today, Sir Michael will discuss the development of modern semiconductor structures to investigate fundamental aspects of physics previously inaccessible with naturally occurring solids. These include the creation of devices where one-dimensional restricted electrons lead to the appearance of a quantized staircase. The transition regime between 1D and 2D will be discussed, whereas confinement weakens, carriers can move to the sides and adopt a zig-zag configuration to decrease inter-electronic repulsion. So Michael will use simple theoretical concepts to explain features arising from this electron configuration, where sometimes electrons appear to have fractional charge. Without any further ado, let's invite Sir Michael to present his talk.
Thank you very much for the invitation. It's very good to be back in Cambridge, and I'd like to tell you about some work which has gone on both here in London and elsewhere on quantum effects using semiconductor nanostructures. And in particular, what is now known about conductance quantization, which is an interesting topic, started off in 1980 with the discovery of the quantum Hall effect and has progressed since then. Can you hear me in the back?
Not much.
I think the microphone is not working.
Is that better? How about this?
Is that better? Not worse?
Can you talk a bit longer?
Try again.
Yeah, I'll count to three. 1, 2, 3.
Yeah.
Okay. How about this? I'll count to 3.
No, it's the same as before. It's not very loud.
No. That's good. So let me just go over some background actually. We're all familiar with electrons. Electrons in orbits around atoms are responsible for chemical bonding. And in solids, when the atoms come together, some electrons are liberated and are free to move through the solid. And that gives us electrical conductivity, which is very important. So quantum mechanics was developed to explain the orbits of electrons around atoms, which was known to be responsible for radiation emitted due to electrons jumping from one level to another. However, in the solid, we have a very different situation. We have electrons colliding with impurities, with defects, with all sorts of material imperfections. And so we've developed various techniques and formulae for handling the conductivity and basically the conduction of electricity. Now, it's not apparent that resistance should be a quantum quantity. As you know, one measures resistance by passing a current through a sample, which can be anything really, and measuring the voltage across it. That's what one does. And the resistance is high if for a given voltage the current is small. And of course resistance can take any particular value depending upon the material we are investigating. So it came as a bit of a surprise when back in the 1960s actually, the resistance as a quantum concept first emerged. Basically that h upon e squared has the dimensions of ohms, and it is known as the quantum of resistance. It's approximately 25.5 kilohms. Usually we refer to the quantum of conductance, which is just the reciprocal, e squared over h. Very often there's a factor of 2, because the quantum of resistance is 1/2 h upon e squared, and that is because we have 2 spin levels. As you know, only one electron could be in a quantum level, but spin up and spin downs are different quantum states. So the quantum of resistance is h upon e squared, but normally we measure 1/2 h upon e squared. And I will show you actually how we can produce a transition. There are various transport regimes, and at the top you'll see here we have essentially what is the normal situation of scattering centres, and the electron diffuses through the solid. If we apply a fairly small voltage to measure the resistance of it, then the electrons can describe what is a classical diffusion with an extremely small drift velocity in the direction of the applied voltage. If, of course, we increase the voltage, then we enter non-ohmic regimes, which are a subject in their own right, which I won't be discussing at the moment. However, if we can reduce the scattering centres, the number of them, then we can go through, this is the case that the scattering length L subscript E is greater than big L, then the electrons can go through ballistically, that is, without any scattering whatsoever. And modern methods of crystal growth have resulted in the ability to make samples which are of the order of something like up to 10 microns in length, in which there is virtually no scattering. Just to give you a comparison, the diameter of a typical human hair is 100 microns. So this gives you an idea of the scale of the lengths we're talking about. And if we have that situation, the ballistic transport, and if we can confine the electrons with a fairly smooth potential, then they will bounce off ballistically, exactly like billiard balls bouncing off the side of a billiard table or snooker table or pool table, whichever game you like. And so that's essentially what is meant by playing snooker or playing pool with electrons, which is a subject in its own right. Actually, interrupt me at any given time, actually, if there's something which isn't clear or you have a comment. Now, over the last 20, 30 years or so, there's been quite a transformation in the type of semiconductors which are used. The typical semiconductor, or the first semiconductor rather, was germanium, which was rapidly superseded by silicon. And the devices which are used for 98% or so of information technology are basically silicon devices. And the first silicon device to really be exploited was the bipolar transistor, which has now been superseded by the MOS transistor. And what this basically is essentially a capacitor structure in which we apply a positive voltage to a capacitor in which one electrode is a metal, we apply a positive voltage to the metal, the other one is a p-type semiconductor in which the majority carrier is the hole, and we attract a thin layer of electrons to the surface. And this is called the inversion layer because we've inverted the polarity of the majority carrier at the surface. And it's contained in a very narrow potential well. So if we have the surface, then we have a potential well. The surface actually is an interface between the silicon and an insulator. And so we will trap the electrons in a very narrow potential well. And that means that the momentum becomes quantized. It cannot move in the direction which is perpendicular to the confinement. And so it can move in a sheet parallel to the interface without having the ability to move in the direction normal to the interface. So basically, I mean, we walk around essentially in a two-dimensional world. We can't go up very high, we can jump up a few feet. If we want to go higher, we go in an aeroplane, but these are pretty small distances. So the electrons here are confined in a two-dimensional sheet. And that means actually that they have different properties. And more recently, for physics experiments, the silicon inversion layer has been superseded by the gallium arsenide structure. The gallium arsenide structure, which is a semiconductor, gallium arsenide has a layer of aluminium gallium arsenide on it, which is a more or less perfect interface, and at low temperatures, that is an insulator. So all I want to say about this, to summarize it, is that we have the ability to produce an electron gas in a very narrow, confining region in which there is very little scattering. And this is an ideal situation for looking at quantum effects. This is a very old slide, actually. I took it because it hasn't been brought up to date. But because of the interest and in producing low disorder semiconductor structures for physics experiments, the idea has arisen, it's a discovery actually, that instead of producing silicon or gallium arsenide or any semiconductor with impurities in, you may recollect those of you who did physics, otherwise let me just explain that if one puts in impurities into the semiconductor, then the impurity can get rid of an electron which is free to move around. That's doping of semiconductors. The only problem with it is, for physics experiments, is that at very low temperatures, the electron bumps into the impurities, and that is a form of scattering, which then basically limits the experimentation and limits the electron mobility. The electron mobility is essentially the velocity of the electron when an electric field is applied. So increasing the mobility arises when the disorder is reduced. And this actually shows what's happened as a function of time. The DEG stands for two-dimensional electron gas. And so you'll see there, that's the temperature. And as we drop the temperature, so the mobility rises because, so I'll just turn my phone off. So the mobility rises because of the absence of scattering. Right at the bottom, you'll see what happens to the bulk. That's a normal crystal. This is a gallium arsenide structure. And essentially, on the left-hand side, that gives you the construction, which we don't have to bother with at the moment. Just let's assume that we can do it. We can produce a two-dimensional electron gas in which we can control the carrier concentration because it's a capacitor structure. And the mobility is very high at low temperatures. And in fact, we can more or less abolish the scattering. So any effect which depends on the way in which electrons interact among themselves can be conveniently studied. But I'd like to go a little bit beyond 2 dimensions and just mention 1 dimension. Now you might think actually 1 dimension is rather an elusive concept actually. Because it means the electron is only free to move in 1 direction. However, these can now be made in the laboratory, and in fact can be set up as in teaching laboratories as experiments for undergraduates. You may even have done one yourself. What I want to do is point out the density of states here. The density of states, let's just say, is in fact the number of allowed energy levels per unit energy. We don't have to go into any more detail. And so down there at the bottom, all I want to point out to you is that in fact it goes as the square root of energy in 3 dimensions. In other words, as the energy of the electron increases, so the number of states available to it increases as the square root of energy. In 2 dimensions, it's a constant, basically. It's a constant, no matter what the energy is. But in 1 dimension, we have the remarkable fact that E minus EC, where EC is the bottom of a band, so it's the minimum allowed energy. E minus EC goes as 1 upon the minus the half. In other words, 1 upon energy to the half. And in a quantum dot, which is a totally confined electron, essentially it just has 1 energy level. That's it. Now, the key here in looking at 1 dimension is the fact that the energy goes, the number of states available goes as 1 upon the square root of energy. And if you do a classic, it's actually m to the half over energy to the half. Now if we just say classically the electron energy is a half mv squared, which is pretty good, it works here, then m to the half over energy to the half is just 1 over the electron velocity. And that is a remarkable fact, which is the key to all the effects I'm going to discuss. Sorry about all this endless. How do we make the wire? Well, what we do is we start off with a piece of semiconductor. Remember, we've got access now to all the paraphernalia and equipment used in the semiconductor industry. So we can make very small structures with no problem whatsoever. So if we start off with a semiconductor structure, in which we have a 2-dimensional sheet of electrons, which is in mauve, purple, or blue, depending actually, usually on projection. And now what we do is on top of it we put metal gates. These are just pieces of metal that we can shape to any desired shape. And so we have a small gap. To give you an idea, the typical length of the gate is about a micron or so, anywhere between 1/2 and 1.5 to 2 microns. Say a micron. Their separation is about 1.5 to 2 microns. And their distance from the electron system is probably about 0.1 or 0.2 microns, but can be varied, of course. And there's an insulator which separates the metal gates from the semiconductor. So we apply a voltage to the gates, but no current flows because of the insulator. And if I now put a negative voltage on these metal gates, I deplete the electrons from underneath. I repel them, they go away, they go to ground. And what we end up with, you'll see there, is a very narrow channel, a constriction. And this is called a quantum wire or quantum point contact, because it's very narrow. In fact, I mean, we can pinch it off completely to 0, and its length is about a micron, 1.5 microns. So if we make this out of the high mobility material we've been discussing, then the electrons can pass through with no scattering whatsoever. They go through ballistically. And we can vary the confinement of them. And because of the quantized nature of the transport at low temperatures, this means that we can set up something like the quantum particle in the box, and we can vary the box size just by changing a voltage in the gate. So this is a quasi-one-dimensional system. We say quasi-1D because we can have many quantum levels occupied. And basically, when we calculate what it looks like, it's essentially parabolic confinement. And you'll see on the left-hand side, that's the wave function and next to it is the probability distribution. If you're not familiar with quantum mechanics, then not to worry. All that tells you about where it's psi y squared is that is the distribution of electrons in the channel. And you'll see the ground state n equals 0. Essentially they're peaked up in the middle, and going up n equals 1, first excited state. There are two modes. So as we now squeeze the electron system, we squeeze it electrostatically by increasing the negative voltage from the gates. So we squeeze them, and the quantum levels go up in energy, because the energy of a quantum level goes as 1 upon the distance squared. They go up in energy, and you see what happens there. We're simulating them as they go through 3 on the scale there, that's milli electron volts for the particular system. They change colour, and that means as they go up, they're past what is termed the Fermi energy, where the probability of occupation is more or less a half. Then essentially they change, and they lose their electrons, and we've simulated that with the change of colour. So you can see there we have 2 levels occupied, and now the first excited one goes up, and we're left with just the ground state there. And if we squeeze that ground state, well, then we'll have nothing. You see here we've gone in this particular figure from 5 levels occupied down to 1, the ground state. So we can manipulate the quantum properties of the electron just by applying a voltage. So in order to ascertain the conductance or current, we need a new formula, because the conventional formulae don't work, because the conventional formulae are based around scattering of electrons, so there's a mean free time between these scattering events. And it's very simple, really. What we will do is we will take the density of states, which we've called D of E, that's the number of allowed energy levels of a particular energy, and that gives us, over an interval, small interval differentially, dE, small d, and if we multiply that by the velocity, then we will get essentially the makings of a formula for the conductivity. And what we find is, if you recall, we said before that the density of states goes as 1 upon the square root of energy, which is 1 upon the velocity, and if we multiply that by the velocity, we get something, a conductance, which just depends upon the fundamental constants. And in fact, the resistance of it is h upon e squared, or if we've got spin degeneracy, 2e squared, 2h upon e squared. So this is what we measure. This is an experiment which was done in the Cavendish a few years ago. You'll see in the insert at the top, that actually just describes the sample. We have a sample like that, S and D, the source and the drain. That's the source of electrons, and D is the drain. So the electrons pass through the system from S to D, and they pass through this constriction, which here we have denoted it by a width W. And what we find is that as we vary that gate voltage, you'll see it goes from -6 to -3. So a very small negative voltage from a battery. And then we remove the electrons, and at -6 volts or so, the conductance, which is G, this is conductance, the inverse of resistance. And you'll see it's in units of 2e squared upon h, because we are spin degenerate. And you'll see a series of plateaus going up. In fact, there are 28 of them that we can measure. And they are, each one of those plateaus is a quantum level. Because when the electron occupancy is in a quantum level, it's a constant. The conductance is a constant. It's just 2e squared over h. It doesn't vary with energy because, as we saw before, there's the cancellation theorem. So every time we enter a new quantum level, then we add another 2e squared upon h, and so we get a staircase there. The insert B, that just shows what happens if you measure the sample from more or less 0 voltage, because initially the channel, or the constriction, I use the words interchangeably, is very wide, so we essentially measure the resistance of everything, And then as we narrow it, the resistance of the channel takes over and we start to get the staircase structure. And that actually was one of the earliest results which were in the field of mesoscopic physics, meso being intermediate between macro and micro, or nanophysics. These are nanostructures, and this was the first major effect for nanostructures. And basically, the whole split gate technology was developed in the Cavendish, and this result was obtained in the Cavendish more or less at the same time as a similar experiment using the same technique at University of Delft. If we now apply a parallel magnetic field, because we want to lift the spin degeneracy, and as you know, in the magnetic field, you lift the degeneracy between positive and negative spins. In other words, if the spin of the electron is oriented in the same direction as the magnetic field, the energy is lowered, and if it's opposed to the direction of the magnetic field, it's raised. So we can now split that spin degeneracy, and you'll see what happens is that the 2e squared upon h drops down to e squared upon h, 0.5 times 2, as we increase that magnetic field to 16 Tesla from 0 Tesla. So we've now really lifted that spin degeneracy, and we can get a lot of interesting effects from the crossing of the levels. But basically, this is really designed just to show you what happens in the presence of a magnetic field. We don't want a magnetic field which is perpendicular to the plane of the electron gas, because that will send the electrons round in circles, and we will have a narrow two-dimensional system, which we don't want. Well, we would like it for some purposes, but not here. These discoveries started a whole range of activities, actually, because all that's happening really is that we are restricting the number of nodes, or the channels, which an electron can adopt as it goes through a narrow constriction. Now, there are other ways of doing this, and this is actually a demonstration, which I think a similar demonstration has been set up at the University of Groningen in Holland. And what happens here is a wire is taken, a regular copper wire is taken, and gripped at two ends, and is slowly stretched at a rate which is linear in time. You see the time there in milliseconds. And what happens is, as that, you think actually, well, what we'll have is we'll have current through the wire, because we're measuring the resistance of it, current through the wire, and we measure current, and then it stops when the wire breaks. But life is not quite so simple as that. It's actually a bit more interesting, because what happens is, as that wire moves towards the breakage point, it then becomes, say, 5 atoms wide, 4, 3, 2, 1, and then snaps. And each atom can carry a channel of current. The electron jumps from atom to atom. And so what we will then find is when we have so few atoms that we can almost count them, then the conductance drops in this way here. So it goes from G naught is just the 2e squared upon h, basically the quantum of conductance for the spin degenerate level. And you can see it goes down in steps. They're not as nice steps as the gallium arsenide that we showed before, but this is a wire and a very simple piece of equipment, and it's done at room temperature. So, whereas the experiment with the gallium arsenide structure was done at ultra-low temperatures in the millikelvin regime and cost probably quite a few £1 million actually in equipment to grow all the lithography and everything. Similar experiments have been done actually with a contact. If you just take a regular contact, like a wire or something, or just a switch that you, if you recall photographs or whatever, how people used to send Morse code. They used to get this is a metal and you just tap it. Well, what happens is if you tap it like that, with a plunger, like that, then of course it doesn't make a flat contact, the tip is actually always reforming itself. You're always distorting that tip. And so when it first touches, it's 1 atom wide, 2, 3, and then many atoms wide. And you can see a similar effect at room temperature with no flux. So I'd just like to talk about now the effects of a strong magnetic field back to 2 dimensions. So the electrons describe a circular motion. The orbital frequency over there is quantized. And the density of states, which remember is constant in 2D, it collapses because the quantization of the orbital frequency takes over. And they're separated by an energy h bar omega. They're called Landau levels after Landau, who first calculated them. They're basically broadened by disorder, and states in the middle are free to move. And I'll show you a figure which actually illustrates this. Now this is quite interesting because this is what happens when you apply a magnetic field to a 2-dimensional electron system, which is fairly free of disorder. And you'll see that we get a circular motion in the middle. The electrons describe circles. And if you've got an impurity or something like that in place, they can then be trapped or localized. But notice what happens at the edges. They bounce at the edges, like that. And they're trying to describe a circular orbit, which is exactly the same, but they actually constitute a current running along the edges. Because they bounce off specularly, like our billiard balls at the side of a billiard table. And down at the bottom we get the same effect. They're moving in the same direction, but the current now flows in the opposite direction. And they're called skipping orbits or edge states. And so the electrons in the middle of the sample, they can be localized. They don't move anywhere. But the ones at the edge constitute a current which flows along the edge. Now, these edge states have a very interesting property, which I don't think anything else, well, there are a few examples of phenomena subsequently discovered. But the interesting thing is what happens if you try to scatter an electron in an edge state. Now, in a conventional system, if we've got a sample, 2-dimension, 1, electron moves along, hits an impurity, it can be scattered off in 2D, in any direction. In 1D, it can be backscattered. Just like that. No problem on that. But what happens now in this regime, because the electrons at the top are constrained to bounce off the walls, and the current is only in one direction. They can't go backwards. If they want to go backwards, they have to come down to the other edge of the sample. And they have to pass through the middle, where the electrons are rotating in circles and can be trapped. Now, the samples in which this effect can be seen can be 1 millimeter wide, 2 millimeters. There's no restriction on the width. And so that means that it's virtually impossible for an electron at that top edge to be scattered down to the bottom edge, because there's no way it can get through. The only way it can get through is by some quantum mechanical tunneling, in which the electron flows through a repulsive potential. That can't occur at these distances. So the electrons at each edge are constrained to move in the same direction. In other words, we have abolished scattering. And we haven't just abolished it to a reasonable approximation. We have abolished it to latest experiments show to something like 1 part in 10 to the 10. It just cannot occur. And that means we've made 1-dimensional systems by virtue of applying the magnetic field, but with the proviso that there is absolutely no restriction on the ballistic nature of the transport. And that gives us the quantum Hall effect, which was first done in 1980s. And that the figure there shows a more recent result. That's the Hall effect. The Hall effect is just actually that if we put on the magnetic field, of course the electrons move in circles, but there tends to be more of them at one edge than the other, so we set up a voltage. And the voltage is the Hall voltage, which is just proportional to the current. So you can assume actually that this is the current flowing through the device as a function of the magnetic field. And every time we increase that magnetic field, it's exactly the same as decreasing the confinement in the 1D system we saw before, that we then move to another quantum level and we just add on. And it goes, in this case, it's a resistance, it jumps up by h upon e squared. And those plateaus are flat to about 1 part in 10 to the 10. In fact, it can't be they can't be measured any better than that. So that is the quantum Hall effect, which is arises from the one-dimensionality of the edge states. And it's essentially used for measuring the standards. If one actually assumes h, one can measure e, or one can measure e if one assumes h. I just wanted to mention this because this has a bearing on something I'm going to discuss right at the end, actually, that in extremely high mobility samples, ultra pure, no scattering whatsoever, the interaction between the electrons gives rise to a entirely new effect, which is superimposed upon the quantum Hall effect, in which we see essentially these plateaus of conductance occurring at fractional values. And formulae have been developed to account for this, and it's based purely upon the way the electrons interact with themselves. In fact, the two effects, which principal effects, which show the electron-electron interaction in detail, are superconductivity and the fractional quantum Hall effect. But I don't want to say any more than that. I just want to say that the fractional effect arises from the interaction between the electrons. But the principal effect comes from the one-dimensionality of the edge states, which arises because they are confined to the edge by the magnetic field, and backscattering or any form of scattering is impossible, and so the true quantum nature of the transport comes through. So I can now say a few words. How are we doing for time? On the topology of the electron gas, because at low values of carrier concentration and a wide channel, the electron-electron repulsion can determine the spatial distribution of the electrons. This is a topic which goes back to the 1930s, when the theoretician Wegener, who had been calculating the cohesive energy and other aspects of metals, wondered what happens if we take an electron system, take a box with electrons in. The electrons are negatively charged, so we have to compensate them with positive charge. And let's smear the positive charge out everywhere. And he came to the conclusion, mathematically, that under certain conditions, the electrons could form a crystal, an electron crystal, in which the repulsion held them into crystalline locations, crystal positions, in exactly the same way as when we take a metal, and the metal at very high temperatures, becomes a liquid, as we cool that down, it solidifies, in which the iron cores, which are positive, take crystalline locations, form a crystal structure, and the whole thing is held together by a background of electrons forming a negatively charged background. So the electron crystal, now termed the Wegener crystal, is just the converse. This has been basically investigated and transformed. It's a theoretical work, very little experimental evidence so far, although possibly in fractional quantum Hall. More recently, people have speculated as to what happens in a one-dimensional wire as there is less confinement. And this shows some calculations of Matt Meyer and co-workers, who start off with confining an electrons, to a single row. And what happens if we reduce the confinement? The electrons repel each other, and they would like to move further apart to reduce the repulsion. But they can't. They're held in by confining potential. So what happens if we reduce the confinement potential, and now the electrons can start to move sideways? Of course, this costs energy because they're going against the electric field which is holding them in. But if the reduction in their repulsion is sufficient, they can do this. And they will then form what is like a zigzag configuration. And eventually, as the confinement is weakened, or we increase the carrier concentration, they split up into two separate rows. There's another example, really. This is just an illustration of what happens. There's the linear array, and there on the right is the zigzag. How can we actually see if we split the electrons into two separate rows? Well, we can take a system in which we essentially inject or focus the electrons from an emitter and collect them in a sample in which we bend them round with a magnetic field. So what we have here is this actually on the left illustrates the zigzag we want to investigate. Now on the right, this is a pattern imposed on a two-dimensional semiconductor, two-dimensional electron gas, and it's rather similar to what we've discussed before. The blue is essentially metal, and so we're reducing or eliminating electrons from below the blue regions, and they then enter the system on the bottom through the grey, but we have a very weak magnetic field of about 1 or 2 kilogauss, 1.2 Tesla, into the plane of the board, and that bends around in a big circle. And if the diameter of the circle is such that we pick them up in the space on top where we have a gap between the metal, then we can actually see them because they build up charge. And from that we can find out about the momentum and the dynamics of the electron system. So it's called electron focusing. And we just bend them round. They are emitted in a very narrow region, they're bent round by the magnetic field, and then they're collected. Now on the top, what happens is we vary that magnetic field until the diameter just fits in. And we get a signal there, B subscript S is actually the appropriate field. So when the field reaches that value, we collect the electrons and we can measure a signal. If it's too big or too small, then the electrons then just bounce off, and we don't get them. If we now inject from two places, and we're assuming we have the same carrier concentration in both locations, then what we will see is we will get two separate peaks corresponding to fitting in the diameter between the emitter there and the collector. So essentially we just have a half circle, semicircle, and we just shift it along to take account of the two centers of injection. So we expect to see this peak widen and split. And here you see the experimental result. This is the top, where we see very strong confinement at the top. That's the signal on the vertical axis, that's the magnetic field. And as you see, as we weaken the confinement, which is coming down, then this peak splits into two. So we can say this is quite good evidence now for the fact that the electron interaction will split the line of electrons into two as that confinement weakens. Now, this is an example of what we can see when we measure the conductance. That's the conductance going up. V is the voltage we've been looking at before. This is the voltage applied to the split gates or pattern gates that we discussed before. So when that's very negative, about somewhere between minus 5.5 and minus 6, we have no conduction. And the extreme left shows what happens when we reduce the negative voltage and we widen the channel and we allow the electrons to actually occupy the higher quantum levels. Now, what we can do is, as well as having our side gates, we can put another insulator on with another gate. And so we can vary the carrier concentration overall. And this is what happens here. Every time we move to the right, you get a new series of plots. That corresponds to a lower carrier concentration and a reduced confinement. So as we go from left to right there, we're just repeating the same experiment, sweeping the confinement energy, or confinement potential, but for lower and lower carrier concentrations and wider confinement. Less confinement, wider channel. And you'll see there, just below -3, we remove the first level, the ground state, disappears, completely disappears, and that's because what we're doing now is the energy levels are now dropping in energy with the reduced confinement, and the second level, which has the apparently shape of a sine wave with two centres of charge, is now performing the lowest energy system. And that actually, when that crosses the ground state, so there's a jump, and then we get the normal situation, but right at the edge there. So it's just before that transition to two-dimensionality. You see how close they are together. And that is another interesting point, because if you think about how we manipulate the electron system with the side gates, basically we're putting on a voltage on the split gates, and we change the location of the electrons, the confinement. But there's a distance. If the charge in the electron charge is heaped up in the middle of the channel, there's a distance between them and the split gate. So this corresponds to a capacitor structure. Now, if the electrons are wider, have a wider distribution, they're nearer the side gates, so we don't have to change that voltage by very much in order to influence their number. It's rather like a capacitor structure where we now have a narrower insulating region. And that's what happens there. They're much closer to the split gates, and so a very small change is required. And that is essentially monitoring or manipulating the new ground state, which comprises, I don't know if it's a zigzag or complete separation, probably a zigzag, but we can't quite prove that. But certainly, essentially, it ties up with the focusing experiment of two centres of charge. There's another example here, actually. This is probably a bit neater, actually. You see there, between -3 and -3.2 volts, they just disappear. And now, very low carrier concentrations, reduced confinement, they close up together. And that's quite a nice example, because you can see there's absolutely no evidence of any scattering, no random structure which would appear due to the electrons being scattered by disorder. It's a nice example of a quantum effect. Now, one of the interesting aspects was, if one goes a little bit further and works in a very narrow region, just between the one-dimensionality and the transition to two-dimensionality, essentially the electron-electron interaction takes over. We completely destroy the quantization due to the confinement. You will see this if you those of you with a physics background, because the confinement energy goes roughly, what is the minimum confinement energy? Well, it goes as 1 upon d squared. That's the quantization. What about the repulsion between the electrons? Well, if the electrons in the zigzag, essentially the maximum distance they can get apart is really the width of the sample, which is 1 upon d. So basically the electrostatic interaction, the ratio of that to the confinement energy is 1 upon the width over 1 upon the width squared, which goes as the width. So the wider the channel, the more the interaction takes over. And what happens is we destroy the evidence of the quantization due to the spatial confinement, and we bring in new effects. And this is what we've seen here, actually. A symmetric potential, there's an extra piece of structure at a half e squared upon h, and there is some structure here in an asymmetric potential. We get quite a lot more, and we get a half, and we get 1/6. Now, of course, they're nowhere near as flat as we would see in the fractional or the quantum Hall effect, And that's because we can never really get rid of any scattering completely in 1D. There's always going to be the odd little defect of how which we scatter. In another semiconductor, indium gallium arsenide, we can see there an interesting feature which is actually a little bit above 0.25. The interesting feature of these is that it has stimulated some theory work in the last couple of years. And this just is putting together various aspects of it. You see on the left we've just reiterated the work on the formation of the zigzag. But the theory of Chaput and Orig is a very interesting theory because they are proposing now that in fact what one can have is if we have a situation where we have two separate channels, two lines of electrons, but one of them has a lower carrier concentration than the other, then what one can get is some sort of entanglement between the two, coherent backscattering, in which the electrons interact. So we have the two channels. Now, above all, what we have to do is to conserve momentum. We must conserve electron momentum. But if one channel, if the electrons in one channel are, say, with K value K1, if they are suddenly backscattered by virtue of the interaction with the other electrons, then the change in momentum is 2K1. Now, this has to be matched by the change in momentum of the other channel, which has to become that we have, if it's K2, then we have NK2. Or in other words, what happens is we have some electrons in one of these levels. Say, for example, here we have, say we have K2. The electron is backscattered. Right. That's a change in momentum of 2K2. And we, in order to match this, we have to have scattering, forward scattering, from K1 to K1, from K1 to minus K1 to K1. So in other words, if N1 electrons are scattered in one direction, then we have to have N2 scattered in the other direction from the other level in order that the change in momentum is zero. And when this happens, they form an entangled state. And that gives rise to the, essentially, there's a formula for it there, and that gives rise to the plateaus which we have seen. So this is in its very early days, but it is an example of the quantum effects which are now being uncovered as a result of the use of the technology, advanced technology, due to basically using all the equipment of the semiconductor industry and the ability to grow very high quality semiconductor crystals in which there's virtually no scattering. And I think on that point there, I'd like to thank you very much for inviting me, and I hope you enjoyed the talk.
Well, thank you very much, Sir Michael, for the amazing and insightful talk. Does anybody have any questions for Sir Michael? Yes.
Thank you. It was a great talk. So I guess I have two questions, I suppose. When you were changing the confinement potential and you were getting the peak splitting, do you know if it's a continuous transition from one-dimensional
Sorry,
to
could
two-dimensional?
you shout?
Is it a continuous transition from one-dimensional to two-dimensional electron gap as you increase the confinement potential?
Yeah, it seems to be. Yeah, it seems to be continuous. No, certainly not first order. Yeah.
And then the second question is, are you able to, with your electron focusing experiment, determine if it's zigzag or the third option that you presented?
Well, the focusing will actually tell us if we have two lines, whether in the static configuration one electron in one line is opposite the gap between two and the other. That we can't say, but we can talk about the existence of the two lines. Going back to your first question about the nature of the transition, as we drop the temperature, so the plateau gradually becomes more accentuated. But very interesting effect both in different semiconductors that at low temperatures, very low temperatures, now we're talking about 8 to 10 millikelvin, it seems as if it's starting to go away. And that may be because we are filling up the states on either side of the Fermi energy, so it just becomes more difficult to backscatter, i.e. the number of empty states is being reduced. But this is a speculation, but that does seem to be occurring.
Thank you.
Anyone else? Yes. Me? Great. Thanks again for the talk. Going back a little bit to the early slides when you were talking about resistance as a quantum